well. So today we describe some new results about the electron g-2 calculations. Which I have done this year. Yes. In general, it's.
If you could speak up a little bit, we just maxed out the volume, and just a little bit louder.
Okay. And this is the anomalous magnetic moment of the electron. If we consider an electron as an intrinsic magnetic moment, mu, which is expressed by this expression with G, which is called geomagnetic ratio. From the Dirac's equation in 28, G was determined to be 2, in good agreement with the experiments of that time. But Cushion Follin in 47 found that the difference G-2 is different from 0, 0.001. They measure using the Zeeman effect, gallium atoms. Schwinger was able in 48 to calculate analytically the expression at the first order in quantum dynamics, this alpha on 2 pi. There is a good agreement for the which is a typical quantum electrodynamic effect. Alpha is the finite structure constant, which whose value is whose inverse is very near to an integer number 137. Historically, the QD contribution can be expanded in a power series of this constant, the finite structure constant, alpha square, alpha to the third, fourth, fifth. Calculus and Kroll were able to calculate in the 50 this coefficient, the coefficient of alpha squared. The values analytically was about minus 2. But in 56, another measure of experimental measure of alpha, of the anomaly, the alpha, was in disagreement with that value. So Peterman and Sortin they recalculate analytically independently that value, found an error, sign error in this calculation, and they determined the real value, which is this one. Then the third order, experimentally, the Michigan group in 71 calculate measured this value with much higher precision. So in order to match this precision is needed the knowledge at least of this term. Levine and Wright were able to calculate a first value of C3, which was in Wolf's agreement. The value was refined for Kinocita in 74. And in the years until 90, for example, this value. And the last numerical value calculated with the Monte Carlo integration. This one, there is a small difference due to a mismatch in the calculation it was found. And this was the analytical, I show you here only the numerical value. Calculated by myself Remid in 96, which is actually is the last of a series of values or calculation, analytical calculation of various Feynman diagrams. Concerning the modern measurement of G-2, they are measured storage a single electron in a pending trap one measure with an electrical dipole and magnetic field axial. The value of the anomaly is due to a ratio of frequencies, the cyclotron, the spin precession, and difference between two. So actually, this measurement can be very precise because of the ratio of frequencies. One need the values, the famous values obtained here by the method in 87, with a precision of 4 parts per billion, which gave the Nobel Prize in 89, and the positron value in same year. There is a very good agreement with check of CPT invariance, and the most recent values are due to Gabriel's Harvard in 2006 for the electron, and this one in 2008 refined 0.2 part per billion. A part per billion precision requires the knowledge of the coefficient of the fourth and the fifth power, as well other contribution, more loop, non-QED, other small contributions. Just to, in general, in the standard model, the whole contribution due to the contribution to quantum electrodynamics plus some small effect due even due to electrodynamics of different leptons, and small contribution to hadronic and weak contribution. The first loop 48, Peterman 96. I have calculated semi-analytically a value of the 4-loop coefficient, the 5-loop in open Kinoshita value of 2017. The mass dependent are known analytically to 2 loops, this one by Land, 3 loops by myself, Remidi, and in the 90s, 4 loops. There is analytic expansion due to Marquardt, Steinhauser, et al. And the 5-loop numerical value due always to the Kinoshita group in 2014. These are the analytical values. The first coefficient, 1/2. The second coefficient, remember the number, this is an expression analytical, which contains this strange function, the value of the zeta function in 0.3. This is the free loop, or the coefficient of the third power of alpha, which is 2 lines of analytical expression, very similar, a bit more complicated, but not too much. These are the final diagrams, just to give you an idea. 1 diagram per loop, 7 diagram on 2 loops, 72 diagram at 3 loops, etc. As for loops, there are 891 diagrams, which I don't show for reason of space. These are the numerical values obtained by Monte Carlo integration by the Kinoshita groups in the years. You see the improvement until the last value of the 2014, and the my high precision result is this one. There is a good agreement with about 0.9 sigma. It's an important independent check. At 5 loop, there are 12,000 diagrams. These are the value obtained only by the Kinoshita group. Just to give an idea, in the expression, the value of the various terms, coefficient alpha, alpha square, third to power, the electrodynamic coefficient terms are dominant. These are small contribution due to small effect to a part of the billion. Alpha, I have shown approximate value before, but the most precise measurement is this one, 100, with a precision of less than 1 part per billion. If you put this value in that expression, you obtain a theoretical value of the anomaly with a precision of 0.2 part per billion. The difference in the result, there is a good agreement, 1.6 sigma. Conversely, one can assume that QED is correct, take the experimental value of alpha, invert that expression of the previous slide, and obtain a value of the fine-tuned structure constant obtained by the experimental value of alpha, this one, which is more precise, because the precise of the experimental values is less than this number. In the codetta least square adjustment of fundamental constant, one uses this value of alpha instead of the experimental value. I have calculated C4 just with 1,100 digits. That's the digits. And so yeah. Why such a precision? Because an analytical calculation like 1, 2 per loop, it is at present out of reach due to the complexity of the analytical expression that I will show you in a moment. So I have decided to calculate these values numerically with very high precision. If you are able to make the correct ansatz of the expression, there is an algorithm, PSLQ, due to Ferguson and Bailey in 1992, which is able to fit an interrelation between real numbers. So you have a real number of your quantity, and an ansatz is a linear combination of a number of constants. This algorithm, if your ansatz is correct, this algorithm is able to find the coefficient or alternative bounds of the size if the relation does not exist. It requires very high precision, at least the number of digits called coefficient multiplied by the number of real numbers. And there is also a parallel version of the algorithm, very useful. Just to give an idea, maybe do you remember the expression at one loop, one number, to loop one line, after loop 2 lines of analytical expression. This is a part of the 4 loop expression, but only a part, 1, 2, 3, 4, 5, 6, 7, 8, 9 lines, plus another piece, and another. Just to give you an idea, these are particular special functions called harmonic polylogarithms. And another, for example, it appears that Catalan is constant in this term. And another, much more complicated. For example, this is just to give an idea of the kind of mathematical quantities which appear in this expression, and so on until the last piece. Now, just to give an idea of the 800 vertex diagram can be obtained inserting photon in this self-mass diagram. Just to give an idea of the complexity of the calculations. Each one of these diagram gives 7, in general, 7 different contributions to the for-loop coefficient. Observation. And the novel is dominated by the QED electrodynamic contribution. The hadronic Moore-Loop vacuum polarization contributes to a very small level, 10 to minus 12. 1, 2, 3 loops QED coefficient are known exactly. The 4 loop QED coefficient is now known near exactly, more than 1,000 digits. The ultimate limit is error in hadronic contribution, which is this value, that corresponds to, for example, to this expression, 0.1 in the fifth power of alpha, or this one. Historically, the checks with experimental independent theoretical results have often highlighted inconsistency and some error which calculation of this size, sometimes it happens in QED contribution. For this reason, for example, an independent calculation in the future of the 5-loop coefficient would be important. Just to give an idea, a vague idea of the method of calculation, the numerical value for the Kinoshi QED, especially with g-manifold contribution and combinations of n-loop 4-dimensional integrals. The Kinoshi group calculation are based on the transformation of this integral in 3n minus 2-dimensional integrals of u-rational function of finite parameters, which are computed using the Monte Carlo routine like Vegas, and needs an enormous amount of computing time to sample adequately the integrals. It's a tremendous work. My method instead consists in 2 phases: the reduction of the contribution to a small number of irreducible d-dimensional integrals, analytical reduction, and the determination of system of different differential equations satisfied by these irreducible integrals, and the calculation, the numerical calculation of this integral, an analytical part and a numerical high precision numerical part. This method allows to obtain the 1,000 digits of C4 and sometimes even almost 10,000 digits for some particular integrals, some particular part of the expression which needed more precision. I know that there is also recently an alternative approach introduced by Volkov, which it is based also on Monte Carlo integration, which seems to compromise it at the 5-loop level. In order to perform the calculation, in 1905 I began writing the RC program called SIS, containing all the necessary ingredients, a simplified fast algebraic manipulator, because invoking repeated form has not negligible time cost. I have used a form for the calculation, all the calculation at the C loops. And my program contains a numerical solver of system of differential equations to calculate these irreducible integrals. And then there is also a library I have written a library of arbitrary precision mathematical routines, integer and floating point, because in the mid-90s GMP, well-known GMP library was still in its infancy, was incomplete, not completely checked. Some more data about SIS, C program of 23,000 lines. In general, it takes the description of the diagrams, so the information about the integral which one must calculate, the integral to calculate, contain a simplified algebraic manipulator, as I mentioned before, which used to solve system identities exactly with arbitrary precision integration, rational polynomials, usual arithmetical functions. Efficient management of system identities about up to the limit of the display test currently to 1/2 billion of identities. Numerical solution of system differential equation up to about almost 1,000 equations, and using arbitrary precision floating point complex number and truncated series in epsilon. All the coefficients are worked down in numerical form, even those of divergent. Then a floating point number precision up to 10,000 digits, because essentially one sums expansion in one variable, so a high precision is easy to obtain. Then arithmetical libraries with the operation arbitrary precision integer, polynomial, rational, arbitrary precision floating point numbers, truncated series in epsilon were written on purpose, independent of all the other available libraries. Then I was forced to modify the program to adapt it to multi-core, multi-node architectures needed to use modern machines. Some parallel versions of the program were written on purpose. An interesting point is I have just to introduce checks, very many checks, a systematic protection of large buffers, input-output with everywhere with CRC or checksum, in order to check continuously every transfer of data, storage. In the years, I have found several subtle corruption. Like, for example, I remember some marginal copying of the non-ACC RAM modules with 1 bit changed per week. It's not easy to detect. Some failure in the system with some blocks corrupted, and so for example, 1 terabyte of data is not easy to detect. This permitted to obtain a result with high reliability. Possible new results, but some quantities which can be derived as from the intermediate results I obtained in my calculation. For example, a precision calculation of the slope, which is the first derivative of the form factor, the second factor. Some, for example, renormalization constant in QD for loop, renormalization constant in QCD, which would require also the calculation of some other quantities, some other integrals, irreducible master integrals, with obviously adequate computing resources. The coefficient of 5 loops is an open question. It will be surely a many years task, but it is not impossible. Last, I want to always acknowledge, because Thomas Berman of the University of Zurich, because the main part of calculation was performed on the cluster ZBox2 and the scheduling supercomputer of the Institute of Theoretical Physics of Zurich, University of Zurich, now unfortunately but decommissioned. Yeah, I'm deeply indebted to Thomas Berman for enabling me to use these facilities. That's all.
So you use these PSQL algorithms to find rational coefficients in front of double, so very large precision numbers. So is it easy to explain how this algorithm works in a few words? You're allowed to answer no.
Yes. Yes. In a sense, it's a search in a lattice of. So the algorithm is able to find combination of linear combination of constants which approximate the value which, in general, an integer relation between real numbers with integer coefficient with approximate 0, because this algorithm is able to make a search on a lattice in order to find various candidates of a solution with bounds which size always reducing smaller and with increasing bounds on the size of the coefficient. It's guaranteed that at a certain point the algorithm is able, if this relation exists, it is guaranteed to found that relation, because it's able to find approximation better and better in the magnitude, in the direction, and the lattice of the integer coefficients. Yes.
Okay, thank you.
Can you use the same method to calculate the anomalous magnetic moment of the muon?
The muon at which contribution? Free loop, for loops? In general? In general. In general, yes, it is. The contribution to the muon, it's in some sense similar. This one, there is a mass-independent part plus a mass-dependent with this one, where instead of this small number, there is a very big number, because the mass-dependent in QED part contains a logarithm with a large coefficient. We are dominant actually at 1, 2, 3 for loops. So in for loops, if I remember, the coefficient is -1, -1.9, the mass-independent term, and the mass dependence is about 128, because there is a power of the logarithm of the ratio of the masses, mass of muon, mass of electron. Yes, it's possible. In a for loop, it is. I thought maybe I have written something. For loops, it is known an analytical expansion in this small relation, an expression with a logarithm and mu in this case, mass of muon from mass of lepton, large ratio number, with the logarithm of the measure, with numerical coefficient obtained with relative some percent on precision, I remember, maybe a bit more, but not too much, not non-analytical limits. It could be possible to use my algorithm to find an analytical or best numerical expansion with logarithmic term in the ratio. This one is normal in the muon case, starting from my result for the electron using the differential equation.